Okay. So yeah, we were talking about images and how we can interpret images as data. And now we're going to be transitioning towards the second module, which is going to be about sort of data, but viewed from the point of view of more of statistics and probability. And this is kind of a nice bridge topic between those two, where we'll look at a matrix as data or data as a matrix and try and analyze it with some of the tools to do with transformations that we've already seen. So let's just recall what we were doing. We want to understand some data in some way. And so we were looking at this kind of matrix, and you'll be looking at this in the homework as well, which I think is going to be released very shortly. So we were looking at outer products. And what is an outer product again? It's just a multiplication table. So we have on, if we look at the first column, we have the numbers from 1 to 10. And then in the second column, we have 2 times that same first column. And in the third column, we have 3 times the same first column. So basically that we have the same information, if you like, in each column of the matrix. And similarly, if you look at each row, we have the same information. Just each row is just a multiple of the previous row. And those multiples can, of course, just be real numbers. They don't have to be integers. So this is what we call, this is basically what we're going to call a rank 1 matrix. So rank 1 matrix is just, what we mean by that is we basically just have one vector worth of information in the matrix. So we just have the same column repeated each time, basically. But we actually have 2 vectors involved. One which is the column, and then one which are this other vector which tells us what the multiple of that first column is in each other column. So we need 2 vectors to store a rank 1 matrix. And then the matrix will actually be produced as this, just taking products of each element of each of the 2 vectors. And so in the homework, you're actually going to make a new Julia type which does this. So inside your object, you will store only 2 vectors, but then when you index into this object, it will behave like a matrix. So it's another example of an abstract array. It's an object which looks to the user like an array, in this case like a matrix. And this is similar to the one hot vector that Alan was talking about last time. That was an object that stored only 2 numbers and looked like a vector when you index into it. And here we have an object that only stores 2 vectors and looks like a matrix when you index into it. So it's a very good example where there are no zeros in this matrix. So it's not a diagonal matrix. It's not sparse. It's not any of the maybe more usual kinds of things that people think about when they think about a matrix with structure. But it definitely has a lot of structure in the sense that we only need a small amount of information to actually reproduce the entire object. Right. Okay. And so, yeah, so we're calling this a rank 1 matrix because it basically just has one column. That's where the 1 comes from, even though we actually need 2 vectors to store it. And so I showed these last time. These are examples, visual examples of that. So flags often have a similar kind of, a sort of low rank structure. So in other words, so for example, rank 2 matrix will be a sum of 2 of these things. And we always get these checkerboard kind of patterns when we look at rank 1 matrices, as we saw last time. So let's just remember what that looks like. Here is a rank 1 matrix, and this sort of checkerboard because, again, in each column each column looks the same, but it's scaled by some number. And so if we draw that with colors, we'll get some kind of repeating colored pattern, and the colors change according to the intensity of, how big the numbers are in each column. Okay. And then when we start adding another one on top, so we start with one rank 1 matrix, and then we add another rank 1 matrix on top of that, we get something like this, and we can see that checkerboard pattern starts to disappear. And at the end of last lecture, Alan was showing, that there's this tool, which we'll come back to later in the lecture, the SVD, a tool from linear algebra and numerical linear algebra, which actually enables us to take a matrix and decompose it into basically a sum of rank 1 matrices. And so that's enabling us basically to sort of extract, given a matrix, to get back to the structure of that matrix. One interpretation of the word structure in that matrix. And then we started to add noise and see what that did. And so now then we started to do this transition away from images and towards data. So we're going to take what we did last time, again, the end was to take rows of the image and think of those as coordinates of some data, right? So we'll just take some sub piece of the image and just look at the numbers that created that sort of image. And then we'll just take the first row of the image as X coordinates and the second row of the image as Y coordinates, and we'll plot those on a normal kind of, scientific computing kind of graph, right? So again, what are we visualizing here? So I'm plotting, each of these points is a column of this two row image, right? So each column has two data points in it, an X coordinate and a Y coordinate, upstairs and downstairs. So the first row is the X coordinates, the second row are the Y coordinates. And I'm just going to plot those as X, Y pairs on my graph. So that's what these points are. And the red points are for the first version, where we just took a single rank 1 matrix, a single multiplication table. And the second version is where we took that same matrix and then added noise to each element separately. So noise just means a random number, distributed in some way. We took a normal distribution, and I think, I don't remember, and with mean 0 basically. And so the points get scatter away from the line, but it's clear that they're close to the line. And so, if you think about this new matrix as just some data that somebody gave you, and you want to understand that data, then the first thing you will do is probably plot the data, and you'll see, the blue curve, right? So if I just remove for a moment this red one, hopefully that'll work. Oh, I removed the wrong one, sorry. So somebody gives you this data and you plot it and you look at it, and you'll probably say, oh, that looks like it basically lies along a straight line. And you would like to find which straight line it is and get some estimate of how far away from the straight line you might be. So that's what we're going to do right now. So let's suppose we don't know that this data comes from this underlying straight line with noise, and we want to actually reconstruct that. And that's the idea. And so, of course, this is the whole subject of statistics, and these days machine learning, which is sort of the same as statistics. That's a big debate. So, so we want to sort of find, what is the best straight line in some sense that fits this data, and then how far away does the cloud of data, go away from the straight line? How can we do that? So, your first reaction might be, oh, well, I've heard of this least squares fitting procedure, where you sort of try a straight line and you drop down, you measure the distance of each, so I choose some straight line, and then I measure the distance of each point from the straight line vertically, in a vertical direction. That's important. That's least squares fitting. And then I take the sum of all of those and I try to minimize the sum of the squares, of all of those distances, the vertical distances to the straight line. So I basically have two parameters of my straight line, an intercept and a slope. And I should have actually done this animation, and exercise, try and do the animation. It's pretty neat to see. And so as you're changing these two parameters, the intercept and the slope of the straight line, the sum of squares of these things will actually be changing, and you're trying to find the value of the intercept and the slope, so two parameters, which minimizes this sum. That's one way you could do it. That's not what we're going to do right now. We're going to do something slightly different, which is to try and minimize the square distances when you take perpendicular distances from the straight line, instead of dropping the straight line vertically. Okay, so it's a different idea, and it's it generalizes nicely. Okay, so let's just think, let's go back to this, add back this straight line. So why did we get a straight line here? Let's just think about that a bit more carefully. So this straight line in red, in the red squares, is the original image. So basically, if I have, I'm saying that, if I have a column in the original image here, let's say it's basically 0.5, 0.2, and another one here that's basically 0.25, 0.1. Well, the fact that they lie on the same straight line through the origin is actually the same as saying that, y divided by x is the same number, a constant. And so all of these have the same, value of y divided by x, because each of them is a multiple of the others, right? So mathematically, you just have, if you have two columns, x1, y1, and x2, y2, and x2 is some constant times x1, and y2 is some constant times y1. Of course, if you now divide y2 by x2, then it's the same as y1 divided by x1, and so they lie on the same straight line with this particular slope. Okay. So how can we actually, go think about this cloud of blue points, and we want to measure its size somehow, basically, right? So how could we? So let me remove it again. How could we actually measure the size of this object? So the first thing you could think of doing might be to take this cloud and just sort of say, oh, what is its width? So that's the first thing we would like to measure, the width of the cloud. And so we're just going to sort of ignore how tall it is for the moment to start with and just calculate its width. So, what would be a natural way to do that? Oh, well, you just find the maximum value here and the minimum value here. And so you subtract them, and that gives you the width of this cloud. But that's actually not such a good idea. Why? Because there might be a point sort of way over, at 100,000 that suddenly somehow got into your data for some reason. So we call that an outlier. That sort of doesn't really belong to the data, and there was some measurement error, or there was some error in transmission of the data or something, or it might even be a real data point actually, but it's sort of away from the main bulk of the data, and so we want to exclude that, or we want to sort of temper, we want to weight how influential that point is in our measurement of how big the data is. So we're actually going to want to use a statistical technique instead of just taking this maximum and minimum. So basically, we want some kind of average measure of how far away these data points are from the center. So the first thing we're going to do is just find where is the center of this cloud. In other words, the mean. So that's just it's another statistical measure. So it's just sort of take the sum of all of the data and divide by the number of data points. And so there is a function mean in Julia to do that. Of course, you can easily define your own, and in fact, you did in the first problem set. So this function mean comes from the statistics standard library, which we imported at the start. Hi, Alan. So what's the first thing we're going to do? Just subtract the mean from each data point. So we just use this broadcast or this pointwise minus. So we have x's and y's are these separate vectors of data, and we'll just take the mean off each of those. And then, so we just get the same cloud. When we plot that, we get the same cloud, but now centered around 0, 0. And now we're in a position where we can do this calculation of the width. So what would a natural way to do that be? You might think, oh, I need some kind of average again. So if I just take the average of this new centered data, if I just take the standard mean, I'll just get 0, because I just, the mean of something minus its mean is 0. So I have to do something a bit more clever, a bit more interesting. So we're thinking of the width. So what we're really doing is taking all of this data and projecting it down perpendicular to this x-axis. In other words, the line y equals 0. So here are the perpendicular projections in these dotted lines. And then we get this new cloud of data, which is just the x coordinates, which just lies along the x-axis. So we want, basically to measure sort of how wide is that in a statistical sense. And so the problem is we have these negative values and positive values, and when we take the mean, they cancel each other out. And so, but if you think about the words, what would you really like to find? You would like to find something like the mean distance from the origin. And so distance we usually think of as a positive number. So these negative numbers over here, we need to convert into positive numbers.
Dave, may I ask a quick question?
Yeah, of course.
So if I look at the x-axis, there are some of these orange circles look darker. I guess that's because there are a lot more points kind of right above.
Yeah, that's a great question. Yeah, so we're using transparency. So each of these orange points is actually this very faint orange color. And then when several of those accumulate on the same place, they overlap and you get a darker orange color. So yeah, the amount of darkness is sort of how many points. So if you look here, for example, there's sort of a quite dark orange. That's because many points are accumulating with roughly the same value of x, and they're just being superposed down here. Yeah, so you get a darker color. So that's some kind of measure. It's like a sort of kind of histogram of how many points are actually at that value of x. Yeah. So that we have to take that into account when we calculate this average.
Just another quick question, Dave. In the code here, I see where x and y got defined, but I don't see where xs got defined.
Okay, it's right here.
Oh, there it is. Okay, very good.
So I just took this image and I took the first
By the way, we have a feature request to Pluto that you can like highlight a variable and see where it's defined. Move to that place. So, for example, if you
so if I'm down here and I see XS, I should be able to sort of click on it and then do something and jump to where it's defined. That would be nice.
Great.
Does that answer your question?
Yes, thank you.
Okay. So yeah, okay, we want to find some. Yeah, I was saying we want the average distance from the origin. And so one way we could do that is to literally take the distance. What is the distance? Is just the absolute value of the data point minus 0 in this case. And so it's just the same as taking the absolute value of all of the x's once I've centered them, and then calculating the mean. And that gives me 0.25, let's say, and that's roughly here. And indeed, if you think about it, basically the data set is sort of symmetrical. It's not actually symmetrical about the, when it's not quite rotationally symmetric, but if you rotate it at 180 degrees, it almost basically lies back on itself. And so we basically have some kind of symmetry. And so if you sort of take these values and just reflect them over this y-axis and land them back on here, then you get a cloud of just positive numbers. We can actually draw that. So let's do that. This one. So I'm just going to take the absolute value of each of them, again, using this dot broadcasting. And that is what the cloud looks like once I've folded it over onto itself. And let me even use a smaller value of alpha so we can see it a bit more clearly. So yeah, I don't know if you can see that. There's a cloud of blue points. And again, some of them are darker. And now we want to find the average of those distances. And it gave me 0.25, which is somewhere like here. And that indeed is sort of halfway along this data set.
Can you do what, can I ask you what you asked me last week? Can you histogram these?
Sure, great idea. Yeah, so
basically, I mean, what I'm hearing you say is you've got some data which in absolute value is between 0.5, roughly, and you're telling me that it's kind of like a quarter, which might be true if it was uniformly distributed. Can I get more bins, or is it? Yeah, so
that's that. There, I have not taken the absolute value, so let me take the absolute value as well, and get something like this. And yeah, so it's quite unevenly distributed, if you like.
I don't know, if you smoothed it out, it might be even.
So humans actually have a pretty bad intuition about what random means. And so this is actually a pretty random, uniform distribution, maybe.
Let's do one last thing. Let's try bins equals 20.
No,
Yeah.
maybe not so uniform. Yeah, there's not, of course, there's not so many at the edge, but apart from that, it's maybe uniform. So we'll be discussing this more in detail, what uniform means, maybe next lecture. Yeah, great idea. And we can do the same with y, of course, and we should probably expect something similar. And again, at the edge, right? So this is, now I've taken the absolute value, so this is both edges actually, and we see that there's definitely fewer values right at the edge. Yeah, okay, so maybe it's not uniform. Anyway, it also depends how exactly I generated the randomness. Okay. So this is just a measure of how many of the points fell in each of these bins, in each of these boxes. So between 0.1 and 0.1 and 0.15, 0.12 or something, how many points, how x coordinate in that range. That's what I'm drawing here. That's this number, the height of the bar. So, so that's one way. We just take the absolute value of these distances. That's actually not the way that we usually do it. We usually take the absolute value, take a different measure of distance, which is this root mean square distance called the standard deviation, which I'm sure many people have heard about. So we literally take these values and square them first, and then take the mean of that. And so again, we can actually draw that. There's something that people do not usually do, but you could do a histogram of the squares, and that looks something like this. So that has a very different kind of shape. It's definitely not uniform. And I don't know, is that some known, that's probably some known distribution as well. Like a chi-squared distribution? I don't know. We'll have to think about what that is. Now we're going to take the mean of that. So why do we square these numbers? Well, basically, it's a way of sort of giving, I was going to say giving less weight to the larger values, but actually maybe it's giving more weight to the larger values. Anyway, it's just a different way of, basically we're giving weight to how far things are away from the origin. And actually, yeah, the data points with larger values are getting more weight than they did before because, well, okay, the values here are less than 1. That's confusing. I guess if they're less than 1, then it's not clear to me what happens. And then, okay, anyway, so that gives us what something called the variance, this mean of the squares of the data once we've centered them around 0. And then we take the square root, and that gives us the standard deviation, which is usually called sigma. And so here I've drawn the same data again, and I've calculated these sigma x and sigma y, and maybe I can add in to this picture lines at sigma x and sigma y. So currently these lines are at 2 sigma x and 2 sigma y, and we see that basically encloses almost all of the data. There are some data points that sort of stick out that are slightly beyond 2 sigma x or 2 sigma y. But so usually if the data has a sort of in some sense a normal distribution, we would expect about 95% of the data to be within a distance 2 sigma of the mean. On 2 sigma on either side.
David, can I imagine that I'm in a class and I have some kind of score on 2 exams, right? Where it looks like on the first exam, my score could never have been better than like 60% out of 100. And on the second exam, the top student only got like 21%, maybe. Is that, and so what you plot is your score on the 2 exams, and you're saying that all the students are pretty much all inside this box. Because the professor always gives you the standard deviation. I mean, that's usually, or the variance, right?
Because what did you say?
You always, every student is familiar with getting, the standard deviation or the variance for exams.
Okay. Oh, I didn't realize that you usually just talk about those. Okay, sure.
I don't know whether people know the precise definition or not, but I know that, it's a standard thing to tell people in a class, what the scores are and what the standard distribution is.
But so, yeah, so if you just do the standard, one standard deviation instead of two, then you'll only expect something like 70% of the data people to be less than one standard deviation away from the mean. And so the sort of good students will be between 1 and 2 standard deviations away, basically. Okay. So, but if we look at this box, so far we've calculated these two numbers, which are the width and the height of this data in some sense, but it's clear that we have not captured all of the information about the data, because these numbers don't tell us how this data is arranged inside this box. It could be going from the top left corner down to the bottom right, and that would mean something very different about how these two tests that Alan was talking about are related. So here you can see that if you did well on one test, you pretty much did well on the other test, but if the data were the other way around, it would be the opposite. If you did well on the theoretical test, you did badly on the practical test, and vice versa, maybe, which was my case. So we want to actually track that relation, or so we call that correlation. But it's basically, is there a relationship between the data? If I know that X is big, do I know that Y is big? Or maybe I know that Y is small if X is big. So how can we actually grab that information from the data? So it's clear that just calculating these two widths that we did so far is not enough. So what could we do instead? Well, we somehow want to sort of rotate our point of view and line up our point of view with the data somehow. And so that's what we're going to do. So of course, there are standard ways to do this in statistics, but we're trying to understand from a computational point of view, what would you want to do? And then how does that relate to what you would do in statistics? So, one idea would be literally, let's rotate our axes. So that's the first thing we want to do. Let's try rotating our axes. So somewhere there's a plot where, so here's a plot of the same data set. And let's start off aligned with the data. So this red arrow is supposed to be a new axis. So I'm literally sort of rotating my head and lining this arrow up along what seems to be the direction of biggest, growth, biggest extent of the data, sorry. And as I then rotate around this axis, and so again, I'm now projecting the data, but I'm projecting it perpendicular to this arrow, or perpendicular to this new axis. So this is different from least squares. And as I rotate round, so I'm also, again, showing the projection of each point on this new axis. And as we rotate round, you can see that the projection changes how wide it is. So basically what I want to do is measure how wide that projection is. And now we know how to measure width of a projection. We're just going to measure the standard deviation, but in that direction. So that's one way we could look at it. We're rotating an axis. But the other way, an alternative way, is equivalent, is instead of rotating the axis, let's rotate the data. So here's the same picture, but now I'm rotating the data. So I'm sort of fixing the horizontal x-axis now as what was the red arrow above, and the data is rotating. It's basically the same, but it maybe it's easier to see in this case, and it's certainly easier to calculate. So again, the same picture, but as I rotate the data around, we measure the width just in the x direction now in this point of view, or along the arrow in the other point of view, and we want to know, well, how does that width change as the angle changes? And so we can plot that curve, and here it is. So this is the variance in direction theta, and you can see it's some kind of sine wave or something like that, sinusoidal, as a function of the angle theta in degrees around the circle. And so in particular, there are two directions where we get the biggest variance, which is when the arrow is pointing along this sort of long axis of the data. And there are two directions where we get the smallest, when it's pointing around, basically perpendicular to that long direction. And so what we need are actually to just extract these values of theta where it takes a maximum value and a minimum value. And so one way of doing that, a computational, thinking kind of way of doing that would be literally, oh, well, I just calculate all this data. Now I literally just find the one which is the max, find the two values which are the maximum, and find the two values which are the minimum. And so when you do that, so this is what I've done here. So there's this argmax function in Julia, which calculates, which tells me which is the maximum, which value in the array gives me the maximum value of, I'm not finding the maximum value yet. I'm finding which position in the array gives me the maximum value. Right, so here I've calculated the variance in each direction, and I'm calculating which one is the maximum. And then I'm taking that, I'm evaluating theta there, and then I'm taking the variance at that point, and that because I need both of those pieces of information to draw this point on this graph, right? Which theta it is, where I am in theta, and what is the value there.
So,
and
some of the folks in the audience may have heard of, probably have heard of fitting a line, the least squares line. I mean, I think
I already talked about that.
Oh, sorry, then I missed that. Okay,
and you're right.
This is not least squares, right? This is something different, right? Because did you mention because we have errors in x and y?
I didn't actually, no.
Yeah, so the key difference is least squares is gimmicked up for when you have no error in the x direction and only what, everything, x is considered fixed, like maybe time or something where you know exactly what time it is. But principal components is what you do when both there are errors in x and in y. So, or uncertainties, I should say, in x and in y. And it's a very commonly used method these days.
Thanks. Good point. Yeah. So, so here I've, again, same data set. It's always the same data set. And then where I've literally taken, vectors at these directions and at these directions that I just calculated numerically just by taking this maximum. And I'm just plotting vectors in those directions in those values, those directions theta, and these lengths are the size that we calculated in each of those directions, I think. Or is it 2 times that? Yeah, 2 times that length. So again, it's 2 sigma in each of those directions. So we have kind of solved the problem of characterizing this data set as in which are the important directions, which is the maximum, which is the minimum, and how big is the data set in those directions, in a quite numerically intensive way. And so another way of visualizing that is actually to put this ellipse on top of the data. So basically what we did is calculate the semi-major axis length of the ellipse and the semi-minor axis length of the ellipse, and then literally draw an ellipse with those semi-major axes and that particular rotation angle. And then we see that basically what we have done is, in some sense, although Alan doesn't like this interpretation, we have fitted an ellipse to that data. Except that we haven't, because there's some data that's outside. So what does it actually mean to fit an ellipse to the data? It's not too clear. And so that's, there are better interpretations where what we actually have is some kind of 2-dimensional bell-shaped curve, normal distribution, and we're fitting that to the data.
I'll accept the fact that ellipse seems to capture most of the blue dots. It's good.
Yeah. So, so we've done this in a pretty numerically intensive way where we sort of rotated this thing around and we calculated all the values and then we took the maximum. Is there a better way to do this? And so the answer is yes, there is, unfortunately. So that is, so this is the idea, the intuitive idea behind this method, principal component analysis. So why is it called that? Because you can think of this sort of this direction that I drew here, that is the principal component, the longest direction. What does that mean? It means if I know, if we sort of change coordinates, if we rotate round and you tell me how far you are along this direction, I basically know everything I need to know about the data point. Not quite, because there's this sort of error in the other direction, or this width of the distribution in the other direction. But basically, I know everything I want to know. I distinguish the data best by moving along this direction. If you just tell me where you are in this other perpendicular direction, I know almost nothing about where you actually lie on this 2-dimensional plane. But if I know the x value, sorry, not the x value, the value along this direction, this long direction, then I know almost everything about where you are on the plane.
So if I might
So
provide,
that explains, sorry?
so if I might provide an interpretation with the two test scores, if I know where I am along the principal component, that is the long red arrow, then, you know, I think I kind of know my standing in the class, right? That if there was one number that kind of captures the two exams, it would be sort of the distance, you know, along that line, right? And then you can ask, what is this perpendicular distance then? That's the detail of, you know, how did I do on my first or second test relative to each other? Maybe less important. It's arguably not as principal a component after all, right? The principal component is probably is the long red arrow, and that tells me how I'm doing in the test in the class.
Yeah, great interpretation. Thanks. Okay, so how can we actually calculate this in some other way? Oh, okay, before we do that, so let's think about what happens in higher dimensions. So far we've just been working in 2 dimensions. We have had data that lives in 2 dimensions. What about if the data lives in 3 dimensions? Then, sorry, I got things out of order. Oh, maybe I just deleted the relevant. I had a visualization of what these rank 1 matrices look like in 1 and 2 dimensions that seems to have disappeared. Sorry about that. Okay, so the answer is that a rank 1 matrix in 3 dimensions, so again, where we have, you know, effectively the same column, now 3-dimensional column, repeated in my matrix a lot of times with different multiples. When I plot that in 3 dimensions, all the points will lie along, again, a line, a single straight line, but now in 3 dimensions that passes through the origin in some direction. And if I add noise, then I'll get some kind of cylinder that surrounds that line with some, you know, points distributed inside the cylinder. Whereas if I take a rank 2 matrix, then what I basically have is some rank 1 matrix pointing in one direction and some rank 1 matrix pointing in another direction. And when I add all the combinations of all the points along each of those lines, I'll get the plane that contains the 2 lines. And then when I add noise to that, I'll get a sort of fat plane, thick plane. That was a nice visualization of that got somehow disappeared. Sorry. Okay, so yeah, so what is the singular value decomposition? So that is the mathematical or numerical technique algorithm that enables us to actually calculate this whole information that we just did of spanning all of these angles in 2 dimensions and to work out which the important directions are. So the singular value decomposition enables us to write any matrix in terms of simple matrices, simpler kinds of matrices. And if we think about linear transformations, we know that any matrix corresponds to a linear transformation. Then what it says is that a linear transformation, any arbitrary linear transformation can be decomposed as first do a rotation, then stretch, then do another rotation. It's pretty surprising that, you know, oh, and I guess there might be reflections as well. Sorry, where I said rotation, it's actually rotation or reflection. So, so if we think about writing that in matrix language, if we have a matrix M, then it's possible to find 3 matrices, U, sigma, and V, such that when we multiply those matrices together, which corresponds to this composition of transformations, we get back the original matrix. And these matrices have particular structure. U and V are both orthogonal matrices, which means they are rotations or reflections. And sigma is a diagonal matrix with just numbers just down the diagonal, which are called the singular values, which are the stretch factors.
And the way I like to describe this thing for 2-dimensional data, I'd like to point out that you've already seen this. If you remember, back when I was doing various transformations of images, you know, I was having a lot of fun, right? Do you remember I was doing warps and I was doing perspective projections. But 2 of the simpler things that I did, if you recall, was I defined a rotation and I also defined an X and Y scaling, right? And so what this says is that every image, every picture of corgis, if you will, or any other picture for that matter, can be written as you remember the compose symbol with the little circle? It could be the composition of rotation, stretching, and rotation. We could have showed it to you in that notebook right there.
Yeah, we probably should have. But what I'm doing now is taking this particular matrix, 2, 1, 1, 1, the famous matrix in the context of dynamical systems, and I'm writing it as the combination of, as I just said, of the rotation, the stretch, and the rotation. And so I'm actually, so what does the rotation matrices look like in 2 dimensions? It's just cos of some angle theta, and then sine of the same angle, and then minus sine of theta and cos of theta. That's what the rotation looks like, and then the stretch looks like sort of some sigma 1 and 0 and sigma 2. So this is what we're actually visualizing right here. So I'm starting with these points in the unit disk. So firstly, we need to know how to sample points randomly inside a unit disk. So one way to do that would be to use polar coordinates, where you say, oh, I need a radius between 0 and 1 and an angle between 0 and 2 pi, and generate points that way. So this we're going to talk about random sampling. So this is maybe a good moment to point out that what happens if we actually do that. So let's say rho, let's say radii r's are going to be random points between 0 and 1, and I'm going to take sort of capital N of those. Let's say 1,000, and then thetas are going to be random angles between 0 and 2 pi. So I'm going to generate n random numbers between 0 and 1. So rand generates, we've seen this already, random, uniform, random numbers between 0 and 1, real numbers, floating point numbers. And then we need to multiply this by 2 pi, element-wise, to get angles between 0 and 2 pi. And so is that going to work? Do I have... I've already used the word thetas. Let's call it thetas in words. Okay, and now we want to take r dot times, what do we want to do? Oh, it's not so easy as I thought. It's going to be r's number I times.
You could go r's dot times cosine dot of thetas and r's dot times sine dot of thetas.
Okay, yeah. Dot times cosine of thetas and r's dot times sine of thetas.
You have to go cosine dot.
Thanks. Cosine dot sine dot. And now I want to plot this. So I'm just going to scatter these positions. And again, I need a ratio equals 1. And what I should see is that effect. Yes, that's what I was looking for. So what is happening there? Let's generate more points. Okay, so hopefully you can see that there are it's denser in the middle and less dense around the edge. So if we did a histogram of how many points have given radius, that's easy to do now because I have the radii. We'll see that there are actually more points. Oh.
No, the radii are uniform. It's a 2-dimensional phenomenon.
Yeah, that's not what I wanted to do. Right. Yes.
If you actually, if you plotted the x coordinates or something, or I don't know. But we all see that it's
yeah. That's a good idea. Let's plot the x coordinates. Yeah.
Even that's not a perfect thing to do. But anyway, we all see that it's darker in the middle. That you just can't take a random radius and a random angle and expect to get it evenly distributed in the disk.
Yeah, and that's the same. If you want to generate, yeah, there we go. Nice. If you want to generate random points, for example, uniformly distributed on the surface of a sphere, it's actually more complicated than you think. You might think you generate random angles theta and phi with spherical coordinates, spherical polars, but that's not actually right.
If you do random latitudes and longitudes, everybody would be on the North and South Pole or something.
Right. Yeah. Okay, so that's not what we do. So what we actually do is generate points uniformly in a box from -1 to 1 that surrounds the disk, and then we reject those that lie outside the disk. So that's called rejection sampling, and it's useful to produce these kind of weird, sample from weird shapes. Okay, so so that's what I've done. So I generated these points in the unit disk. And then, so let's start. Yeah. And so now what we're going to do is we're going to work up to that transformation 2, 1, 1, 1, bit by bit. And so I've got this slider, which is starting at the identity transform and ending at this 2, 1, 1, 1. And as we move the slider, it's a bit slow, but this circle sort of, on the left, I'm just looking at the stretch component of this transformation. And on the right, I'm stretching it and rotating it. In other words, I'm applying this transformation, the matrix M, basically to all the points, to each point in the unit disk. So as Alan said, we could, of course, do this with corgis, and that would be nice. But I think it's also nice to not have the corgis in the way. And just to think
that have corgis in the way? Okay.
So, we're getting this kind of picture of Saturn on one plane, and then this is actually what Saturn looks like, rotated when you look at it. Yeah. So how am I calculating these stretch factors? Right. So you can see that the effect of applying the whole matrix is, visually, it's clear that it is. I'm stretching the y coordinate by this particular factor and the x coordinate by that other factor. I'm squashing the x, sorry, the other way around. I'm stretching x, I'm squashing y, and then I'm taking the result and I'm rotating it. And that gives me the effect of the full transformation. So how am I calculating those stretch factors? That is what this, that's what we did before by scanning all the directions and choosing the maximum one and the minimum one. But now I'm doing it using this algorithm called the singular value decomposition. So I'm literally taking the singular value decomposition of this matrix, and that gives me back 3 matrices. So let's look at those matrices. So I've got my matrix 2, 1, 1, 1, and I'm taking the SVD of it, and I forgot to mention it. And so what it returns are 3 things: the U factor, which is this 2 by 2 matrix, the a vector of 2 singular values, just numbers, and positive numbers, and this other matrix here. And so if we look at these 2 matrices, in this particular case, I chose a symmetric matrix. Maybe that wasn't the best idea. Let's, we can also choose a non-symmetric matrix or whatever. And so these are actually, the columns of this U matrix are pointing in the directions of this maximum and minimum stretching factors.
So if I might just sort of interject just a little, I mean, I don't, some of you may have taken a linear algebra class, maybe yes, maybe no, or maybe you will someday. And you might hear about the singular value decomposition. And you'll hear about it being connected to these scary things called eigenvalues. They're probably not that scary. But in a way, when we think about computational thinking, I think it's more interesting to just sort of see what this SVD thing does. I mean, it's kind of nice to drill down and get the whole math of it all. And you can get that in a linear algebra class. But really, I think when you just experiment with the computer and you see that a circle is becoming an ellipse, and there's 2 stretch factors, one in one direction, one in the other, right? If you look at the ellipse that's on the right, the Saturn on the right, I mean, it's clear that there's an ellipse. It's specified by the lengths of the axes and the directions of the axes. And simply put, the SVD is giving you that information, right? I mean, if you take a linear algebra class, you learn how to calculate it. You could get an A on your exam by, calculating the eigenvalues. But you may or may not get the intuition of the thing, but hopefully you will. But it's the stretching of the data in this case that is completely captured by the SVD, and that's why it is so critical for the statistical approach of principal components analysis.
Yeah, thanks. Yeah, because basically the stretching is somehow the main thing that's going on, and there's rotation. It's sort of like changing coordinates. Yeah, so these singular values are the distances that it got stretched. So here we see 2.6 and 0.38. And if we look at this left-hand picture, we see indeed that this sort of extremum of the ellipse landed around 2.6, and this one landed around 0.4. And so this is actually capturing these stretching factors. And these, as I said, these columns of this U matrix are giving me the vectors, unit vectors pointing in the directions of the maximum that correspond to those stretching factors. So just to finish off the class, so this SVD applies to any matrix, and we have a matrix that is actually in 2 times 300. That's the size of this image matrix. If I just look at the matrix, it's 2 rows and 300 columns, and so we can take the SVD of that matrix. And so what is that doing? It's sort of telling us how to think of that matrix. What is the effect of that matrix? Is it actually, in some sense, we are working in 300 dimensions. So another way of thinking about this matrix is that instead of 300 points in 2 dimensions, it's 2 points in 300 dimensions. And so that's somehow what transpose is doing. If we took this matrix and thought of it as 2 columns of 300 points, then we're now we have 2 points in 300 dimensions. And so what we can do is actually do a rotation in 300 dimensions.
That really boggles my mind that that there's like a duality between 300 points in 2 dimensions and, which, I mean, it seems like a lot of points, but I could kind of see it in front of my eyes, or 2 points in 300 dimensions, which in a way sounds simpler, like it's only 2 points, but, I can't see it in front of my eyes, like 300 dimensions, who could see that? Right, but it's amazing that you can go back and forth, and they're both sort of, the math doesn't care. It's kind of the same thing to the math. That boggles my mind. So maybe you might think about that a little bit.
Yeah, indeed. Yeah. So what can we do? So in the SVD, we have this other matrix V that we actually sort of did not capture in the pictures that we've just been looking at, and that's another rotation. And in this case, it's going to be a rotation in those 300 dimensions. And so how can we actually, what does that even mean? It sort of literally means you're in 300 dimensions and you'll just sort of rotate your head a bit. But you're doing a transformation which preserves all the lengths or whatever in 300 dimensions. And so we can actually generate one of those things. So first we're going to generate a random matrix in 300 dimensions, 300 by 300. And then we're going to make it antisymmetric by subtracting the transpose of that matrix. And so that it looks like this. And so we transpose it, so we flip X and Y in the matrix. And then we subtract one from the other, and we see that indeed we get zeros all along the diagonal. And then it's antisymmetric, which means that the ij element is minus the ji element. And you can see that that's the case for all of these elements that you can see. And then we do something called the matrix exponential on that antisymmetric matrix, and that actually gives us an orthogonal. Let's rotate. And so the result looks like this. So if we start at 0, so we have again a sort of a path of matrices in this space. I don't know why sometimes it does this, where you can't actually see the picture. Oh, no. Strange. So here we go. So this is the same cloud of data yet again, 300 points in 2 dimensions, but now we're thinking of it in this 300 dimensional space, and we're going to rotate around in that space and see what it looks like as I move this slider. So you can see that the points are sort of starting to sort of dance around. So each one moves away from where it originally was, and it looks kind of like it's some kind of rotation, but we're actually projecting from. Sorry?
I feel like it's celestial, like.
Yeah.
The asteroids are rotating around the.
Right, this is sort of like the stars in the sky, and we're seeing one of these time-lapse photos every day as they move around, but they're moving around, sort of each somehow independently, and that's what we're seeing here. So this is actually a projection of the.
You couldn't visualize a rotation in 300 dimensions. You can go and say, "Oh, I just saw one."
So what we're seeing is, somehow a projection from the 300 dimensional space down to these 2 dimensions. Okay, so I guess we've run out of time. So yeah, so from now on, we'll be talking more about these random. How do you generate random objects? What does that mean? And how do you analyze randomness using probability theory and some statistics and apply that to data analysis? Okay, see you on Wednesday.
Okay. Have you disconnected?